going on page 31 when we're done. So we're going to look at tests for symmetry, and then even and odd functions is tomorrow, all right? So we're going to look at the graphs and the types of symmetry that these graphs have. Now, we talked about notation and being precise with our language and our, saying what we mean, that sort of thing. Then these first two sentences on these notes are like elementary level descriptions, and it drives me nuts. So we're going to fix them and make them truly academic language in what we're doing, because we need to be able to understand it better than this. But if you look at these first two, these two graphs have symmetry. Would you agree with that? Okay, they have and it's the kind of symmetry that you've looked at and talked about since elementary school. So this says the graph can be folded along a line such that the two halves match. Well, when you first learn it in elementary school, that may be how they talk about it. You can even take something, and maybe you did like an art thing where you put some paint, like finger paints on one side, and then you fold it in half and you opened it up and it was symmetric, or it looked like it reflected, right? Did you ever do that? Okay. I don't mean like yesterday, I mean like way long time ago. But you can do that, and it's like how you can make a butterfly or whatever. But it's not really a folding that's happening here. So we're not going to talk about it being folded along a line. So we're going to mark that out. This graph right here is related to the x-axis how? What can I say I could do with this graph in the x-axis? Reflect it. So if I took this graph, right, and this was my line of reflection, and I reflected it across the x-axis, it would just land back down where it was, right? If you pretend like there was like a groove dug out of here, and you were able to pick that up and reflect it over it and then set it, it would just set right back down in that same groove, and you wouldn't even be able to tell anything happened. Does that make sense to you? Okay, so it's a reflection. It's not a folding. You don't take the top half and fold it to make the bottom half. That's not what's happening. So instead of being folded along, it can be reflected across a line. Okay, turn the sound off or put it on airplane mode or whatever's dinging. Reflected across a line such that, and not that the two halves match. Okay, am I hearing things, or is there like noise happening here? Am I just crazy? What is that, you? Okay, it's not very smart. Turn it off. All right, so the graph can be reflected across the line so that it coincides with itself. So let's talk about that big word there. It's like a $5 word, right? When you graphed lines in algebra, you could have lines that were coinciding. They could be parallel or intersecting or coinciding. So a coinciding line would be like when your equations looked different, but you graphed the line and then you graphed what you thought was another line and it just graphed right on top of it, right? So it was actually the same one. Those two lines coincided. So if you have two things planned and they coincide with each other, then they're at the exact same time. So that's what's happening here with that little groove, right? If I pick this up and I reflect it and I put it back down, it's coinciding with itself, basically saying it's going to look exactly like it does right now. You with me on that? So this right here, this one is a reflection in the x-axis. Okay, and that wording is weird, but it's correct. And so you can say it a few different ways. You can say that you reflect it across the line, or in the line, or through the line even. And I know in sounds weird, but that's why I had you write that one. But it is a correct way to say it. Okay, so you reflect it in the line even though you can't get in the line, I know. And then this is a reflection in the y-axis. So that kind of symmetry is the kind of symmetry that you are most familiar with and have seen the most throughout your school career. And it can be called reflectional symmetry or line symmetry. Okay, so we're going to use line symmetry because there's a line of symmetry, right? In this case, the line of symmetry is the x-axis. In this case, the line of symmetry is the y-axis. Okay, easy enough? So then when you get into high school geometry, we can't just talk about it as symmetry anymore because there's other kinds of symmetry besides line symmetry. And what you should have learned in geometry is that you have also something called rotational symmetry. So one of the things that I do in my classes is we get out those little the shape sorting toys that little toddlers use, you know, and like the little Tupperware things, and you can take the little star and you can put it in there and you can turn it, right? You can turn it different ways. And since I can place it in the little toy this way, or I could turn it and place it in again, it has rotational symmetry. So you can rotate through a number of different angles, anything between 0 and 360. But if you can rotate something 180 degrees specifically, even if it has other angles in there, then it has a special kind of symmetry that is this 180 right here. But this sentence is bad too, because this says the graph remains unchanged when rotated 180 degrees about a point. Well, if you rotated 180 degrees, is it unchanged? No, because you just changed it, right? Like the sentence itself doesn't even make any sense. So instead of remains unchanged, we're going to say looks unchanged. And the reason it looks unchanged is because it coincides with itself. So if you look at this graph, and then you take your paper, and you turn it 180 degrees, it should look the same, right? It should look unchanged, but clearly I just changed it because now it's upside down, right? So does that make sense to you? Even though this is rotational symmetry, the rotational symmetry that goes 80 degrees is called point symmetry. Right? So reflectional and rotational symmetry, there's your transformations that you do in geometry and even geometry stuff before high school. But then that gives us line symmetry and point symmetry to look at with our graphs. Okay, we all good so far? All right. So the x-axis and y-axis are common lines of symmetry, and the origin is a common point of symmetry. So it's said that way because really a graph could have a line of symmetry that could be any line, but we only care about x and y axis right now. We could have rotational symmetry, and the point of rotation could be anywhere, but we only care about the origin. What's the origin? 0, 0. This is the origin, 0, 0, right? So let's run origin, which is 0, 0. Should we know that? Yes. Should we know a lot of things that were a crazy hot mess on your quiz? Yes. It was a little sad. Okay, so yes, but I want to make sure. If you have a question, ask, because you're probably not the only one thinking it. I'm not going to make you feel stupid if you ask a question. Okay? So please, it's fine. All right, everybody good so far? So let's see how this works. It says the following graphical and algebraic tests can be used to determine if the graph of a relation is symmetric to the x-axis, y-axis, and or the origin. Oops, I should. Let's look at the graphical test first. For x-axis, it says for every point x, y on the graph, the point blank is also on the graph. So in geometry, we reflected things, right? And they were probably mainly shapes, maybe triangles, rectangles, I don't know. You had them on the coordinate plane, you looked at the ordered pairs. Well, the purpose of that wasn't just so you could reflect a shape, because again, you may never have to reflect a triangle again ever in your life, but we were doing that to see what the patterns were, which you also learned in 8th grade math, by the way, so it was already a repeat when you got to high school geometry, but you do that for this. This is where we're getting to. I think y'all go into your different math classes and you think like these are completely unrelated, and that's not true at all. They are completely related, and we got to tie them all together. Bless you. So when your rule for reflecting in the x-axis, you either change x or y, but not both. So here's how you make sure you got it right in your head. If I look at this, if I take this point, I'm going to reflect it here in the x-axis. What doesn't change? The x value. Clearly the x value is exactly the same, right? The y value changes, but what's the only thing that changes about it? The positive or negative. So it's technically the sign, because if it's negative, then it becomes positive, right? So you change the sign. So for every x, y, the point x negative y is also on the graph. So that's the only thing you have to do is change the sign on y. You've reflected it across the x-axis. So that's graphically if you're going to go graph those points, which sometimes you might have done by counting, right? But then the algebraic test, if I'm doing it strictly from an equation, then what I do is I replace y with negative y. And then after I simplify it, if I get equivalent equations, that means it has x-axis symmetry. Okay? And we'll do some examples about that. So if that doesn't really make sense to you, it's okay. We good so far? So if I have y-axis symmetry for every point xy, well, if I'm going to reflect in the x-axis, I change the sign on y. So if I'm going to reflect in the y-axis, what do I change? The x. So it's negative x, y. My algebraic test is to replace the x with negative x. Okay, so now let's talk about the origin. So one thing you may or may not have learned in geometry, I don't know if y'all all did compositions or not, but if I have a point, if I'm going to reflect twice in intersecting lines, it's the same as a rotation. So if I have this point here, and these are my axes, right, and they're perpendicular, so that's 90 degrees. So if I take this point and I reflect it in the y-axis, it'll end up somewhere over here, right? And then if I take that point and reflect it in the x-axis, it's going to end up somewhere down there. So I just did two reflections in intersecting lines. That's the same as me taking this point right here and rotating it 180 degrees. Okay? Does that make sense to you? So that's the same as just reflecting it twice. So if I take my original point and I reflect it in the y-axis, I change the sign on x. Then I take that and reflect it in the x-axis, I change the sign on y. So when you rotate about the origin 180 degrees, what is this going to look like? Negative x, negative y. You just change the sign on both. Okay? Does that make sense? We're good? All right. So my algebraic test here then is to replace x with negative x and y with negative y, and see if you get equivalent equations. Everybody good so far? Any questions? Okay. So if I just gave you an equation and I said, what type of symmetry does it have? And you had nothing to go by to kind of guide you, then you would have to do all three of these things and check all three of them out. But these start you with graphs. So since this is starting me with a graph, I have at least a starting point, because I can look at that and I can tell by looking what type of symmetry I think it has. Does it have any? Yes. What kind of symmetry does it have? Line symmetry. And what would my line of symmetry be? The y-axis. So that means my choices are x-axis, y-axis, origin, or none. So it doesn't have origin symmetry, because if I rotate it 180 degrees, it just looks upside down. But this is my line of symmetry here. That is the y-axis, so it's y-axis symmetry. The second part of the instructions says to confirm your answer algebraically. So our algebraic test for y-axis symmetry, what do I replace? The x. I replace x with what? Negative x. So that means I'm going to have y equals negative x to the fourth minus 4 squared. Did I substitute that in correctly? Parentheses, right? You may know what my intention is. I may know what your intention is, but what I'm saying here is not actually correct. When I substitute that in, I don't want x to be taken to the fourth power. I want negative x to be taken to the fourth power. And y'all remember that that's different, right? If I have negative 5 squared, that's negative 25. If I have negative 5 squared, that's positive, oh my gosh, 25. Does that make sense? You see the difference there? So my intention is it's the negative x that I actually want squared there, or take it to the fourth power. So then I have this, so now I have to simplify it. It's not that bad. Sign errors are the most common type of errors, and that's what this is all about, is fixing the signs, so we got to be careful. So what is negative x to the fourth power? It's positive x to the fourth power. Do we all understand why? Doesn't that mean this is the same as negative x times negative x times negative x times negative x, right? So times a negative is a positive, times a negative is a negative, times a negative is a positive. So anything to an even exponent comes out positive, whether it was positive or negative going in. So this is positive x to the fourth minus 4, and then negative x squared is what? Positive x squared. So that's what I get after I substitute in the negative x and simplify. Is this equivalent to this? Yes. And so, bam, I just showed that those are equivalent equations. Okay? Does that make sense to you? Any questions at this point? Okay.
So simply multiplying and you wrote 4 of the x's, how can you still lift the exponent if it's already been multiplied?
Well, because if I split that up, this does become x to the 4th. If it was an actual number here, see how my number changed because I used the exponent? Since I don't know what x is, when I put them all together, that just represents x to the 4th. Okay, this is positive. Does that make sense? Okay, good question. Anything else? Yes? Okay, we're good. All right, so look at number 2. Does number 2 have line symmetry? Okay, it does. It's kind of a trick question. I don't really mean to. It has line symmetry. Like there's a line of symmetry right here. But is that a line of symmetry we care about right now? No. So the real question here that matters is, does it have x-axis or y-axis symmetry? No. Does it have origin symmetry? Yes. And if you're unsure, take a good look at it, rotate it upside down, see if it looks the same. And it does. So it has origin symmetry. So to my test for origin symmetry, what do I replace? Good. So x becomes negative x and y becomes negative y equals 6, right? So what is negative x times negative y? Positive xy. And that equals 6. These match, and that's what I want. Okay? So here's what some of you may be thinking already or probably will be eventually. You may be thinking, well, clearly I can look at that, and when I substitute in a negative x and a negative y, obviously that's going to be xy. Like, do I have to actually write this? And the answer to that is yes. Is it because I said so? No. It's because it says confirm your answer algebraically. That's what you're doing here. Your work is your answer, and you can't skip either one of these steps. You have to show that you substituted it in, and then you have to show that you get the same thing. Does that make sense? There's not 1,000 steps. It's not that bad. You just have to understand signs. It's really not that bad. Okay? Any questions? All right. Let's do a couple more together, and then I'll let you work on some. All right. So let's look at number 3. First of all, number 3, that shape, give me, what's the big boy and girl name for that shape? An oval's not the big boy and girl word. It starts with an E. Ellipse. Good. I heard somebody say it. It's an ellipse. It's not and it's not an eclipse. I've heard that a lot today. That's with the sun and the moon. Not the same thing. But this is an ellipse. All right. So this is an ellipse. It's a big boy and girl way to say oval. So if I was to take that ellipse off the graph, so I'm holding it in my hands, it's not on a grid. Does it have line symmetry? So like here's my ellipse all by itself, not on a grid. Does it have line symmetry? Yes. I got a line of symmetry here and here, right? Does it have point symmetry? Yes. If I rotated it, if that was really the middle, then I rotate it 180 degrees, it's going to look the same, right? So it has all those things. But does it have origin symmetry? No, because the center of rotation isn't the origin, right? It has rotational symmetry, but I don't care. Which one of these two does it actually have? X-axis. Okay, so this has just the x-axis symmetry. All right, and then, so for x-axis, what do I replace? The y. Okay, so this is 4 times x plus 3 squared plus negative y squared equals 16. Now, do I need to multiply all this out? No, I don't. And you need to know when you need to do those things and when you don't. Your end goal is not to solve for x. It's not to get a different form of whatever. It's to make it match this. So if this part already matches, leave it. Could I multiply it out? Yes, but there's absolutely no reason to do that. And that's what I saw some on that quiz too, is that y'all would get to one point and then you were done, but then you just like kept doing. It's like sometimes because you're unsure what to do, you just do math when you can see you do math, but you don't really know why you're doing it. And so you don't even know when to stop. We've got to learn when to stop so we're not doing too much and so that we can get things figured out, okay? So I'm just going to leave this first part. 4 times x plus 3 squared. Plus, what's negative y squared? y squared equals 16. And then those match. That's good. Okay. Everybody good so far? All right, look at number 4. Does it have x-axis symmetry? Yes. Does it have y-axis symmetry? Yes. Does it have origin symmetry? Yes. It's got all 3. And so since it has all 3, I have to show algebraically all 3, which is not that big of a deal. Is this really that hard? No. So we don't complain when it's hard. We just do it even if there's a line. It's fine. We move on. All right. So, or we don't complain when it's easy is what I'm going to say. So I don't have to relabel. Like I can't just randomly do stuff. I have to make sure it's labeled since I'm doing more than one. So an easy way to do that is I'm just going to number these 1, 2, and 3 so I don't have to use the words. Less writing, right? And so we'll start with the first one. And I'm going to confirm the x-axis symmetry, which means I replace x or y. Which one? Y. So this is going to be negative y squared minus x squared equals 1. And so either it needs to be labeled correctly, like matched up, or literally say x-axis there so I know which one you're trying to confirm. Otherwise, if you're just, again, randomly doing stuff, I don't know that you know which one goes with what. So this gives you y squared minus x squared equals 1. And that's awesome. Right? So then the second one, y-axis, which means this time I replace the x. So that's going to give me y squared minus x squared equals 1, which is what you expect, right? And if you didn't get that, then maybe you were wrong about what it had. Keep that in mind. Then for origin, I replace them both, right? So this is going to be negative y squared minus negative x squared equals 1. And then that also gives me y squared minus x squared equals 1. So I have confirmed all 3 of them. Okay. Any questions about that? Because when you replace them both, you're confirming origin. And it has a y-axis and x-axis also, so I have to confirm those 2. So you have to do them separately. And I understand that like when you do that, it kind of shows you both, but that may not happen every time, and so you have to just go through the process. Yes?
I'm still a bit confused on the origin. I understood this one, but this one's a little different.
Okay, so if you not understanding from the picture or from the equation?
Well, I understand the x-axis, is from...
Okay, so it's going to rotate about this point 180 degrees. So if I take this graph and I rotate it 100 degrees, which I can't rotate my board, but you can rotate your paper. So like turn your paper upside down and then look at your graph and look at mine. Do they look the same? Yes, and then that's your origin symmetry there. Okay, it's a rotation of 180 degrees. Okay, anything else? All right, I'm going to give you a couple minutes. I want you to do 5 and 6. None of y'all got a phone with you? I don't believe that. So on number 5, does it have any kind of line symmetry? Like, can I reflect it in a line and it look the same? No. Does it have rotational symmetry? It does, but this is my center of rotation, right? If I use the x-axis as a line of symmetry, when I reflect it, it's not going to look the same. Y-axis is not going to look the same. If I rotate it about the origin, is it going to look the same? It's not, because look, this point is 1, 0. If you rotate it in the origin, then it's going to be over here, and it's not the same thing, right? So it has the point of rotation is not the origin, so this one is none. It does not have, it has rotational symmetry, but it is not origin symmetry. If that center of rotation is not the origin, then we don't care. Okay, doesn't count. We good? All right, so look at number 6. X-axis, y-axis, origin, or none? Y-axis. This is my line of symmetry, right? So that means I replace the x. So this is y equals negative absolute value of negative x minus 2. So what is the absolute value of negative x? X. So negative absolute value of x minus 2. And these are equivalent. Okay. We okay with that? Easy enough? Any questions at all?
When y isn't in the equation, do you still replace and say like for this one right here?
Oh, why did I gave you the homework? I didn't intend to give you the homework. I'm so sorry, but go ahead and ask me.
Like you know how y isn't in the equation? Do you still replace it with negative y?
Yes, but it is in the equation. It's just on the left-hand side. Okay, yeah. All right, so since I already gave you the assignment, I don't know, I just did that out of habit because I finished the whole thing with the other classes because I went faster. But I'm going to just let you keep it. Don't even look at the back. The front, you have enough notes. If you want to start on the front, it actually would be a good idea because I kind of just couldn't decide whether or not I wanted to give it to you, and I guess I decided for myself and didn't realize it. I do the work on the front. That way, if you have questions like that, which I will address more tomorrow for sure, we'll work through that one together. But work through it. That way, if you have any questions, don't even look at the back. I don't want you to confuse yourself. We'll finish that tomorrow. Does that make sense to you? We good? Okay, awesome. I'm